So this example problem is a hot water flowing inside a pipe and the cold air flowing outside the pipe across the pipe. And what is given is the hot water inside the pipe temperature. The inlet temperature is at 60 C, and the velocity is at 0.02 meter, at 2 centimeters a second. And the cold air also know the temperature and 10 C and the velocity 1 meter per second. The pipe dimension is 2 centimeters in diameter and 20 centimeters long. So what it asks you is to find out what is the temperature of the water, hot water, at the exit. In other words, how cold the water can be cooled down from 60 C after flowing through this 20 centimeter pipe, and what is the total loss. So again, just write a few things. So we know that this is the hot water, but however, this hot water temperature is at the entrance. So we know the hot water at the entrance, but we want to find out the hot water at the outlet. And we know the cold air velocity, cold well temperature. So this is 10 C and 1 meter per second. And we also know the velocity of the water and the diameter size of the pipe. So now, if we construct a thermal circuit, then we would have hot water, then the air outside the pipe, and the heat is transferring from hot water to the air. And it will go through a few processes. It will transfer from the hot water to the pipe, through convection. So it is the convection. I just write the resistor directly instead of saying convection. So it is the resistance of the thermal resistance of the convection inside the pipe. And there is also, and then the heat will go across the pipe and then go to the air. And from the pipe to the air, it is also by convection outside. And in the past, we usually have a conduction across the pipe, that is across the thickness of the pipe. But however, the problem does not give us any thickness of the pipe. So I would here say ignore pipe thickness. In other words, the surface temperature of the pipe inside the pipe, or the inner surface of the pipe, is the same as the surface temperature on the outer surface of the pipe. and therefore there is only 2 resistance. If we cannot ignore this thickness, then we will have 3 resistance. And then in order to calculate the conduction resistance of the pipe, it will be cylindrical coordinate. And it will also require the material property of the pipe itself, either copper or stainless steel or iron or whatever it is. We need the conduction coefficient of that pipe material. All right, then here, from this circuit, we know that the heat is going from the hot water to the air. And what it asks you is to calculate the total heat loss and then the outlet temperature of the worm. So we need to calculate the Q. We need to calculate the Q. And then the Q will be able to tell us the Q equals to the mCp. That is the total amount of the heat transferred equals to the total amount of the heat to heat up or to cool down the water. Heat up or cool down. Heat up the air or cool down the water. So that would be the mean temperature out minus mean temperature in. And this heat, actually the way that I write is the out temperature minus the in, so that would be the heat to the hot water. And then actually it is minus because we are having the Q leaving the water instead of given to the water. So let me just flip them over. If you don't flip them over, you can just put a minus sign on the Q. Minus Q equals to this. And then if we know the Q, we will be able to calculate this temperature at the outlet. Oh, we didn't use mean. You can use the mean, doesn't matter, but I keep using the same notation here, the hot water outlet minus hot water inlet. And then in order to calculate the Q, then Q will be equal to the convection transfer rate, right? So that will equal to the H hot water average convection coefficient at the water side times the surface area, and then times the temperature difference. The temperature difference is here, it's internal flow, so it is log mean temperature difference. And then this would equal to the air times the surface area, and then times the temperature difference, that is the surface temperature minus the air. The air, you can just write T air, or you can say T infinite, doesn't really matter. That's the outer temperature. And if you want to write the other way, you can also write a overall heat transfer rate constant coefficient times the surface area, and then times the log mean. But however, this log mean will be between the air and the water, and the first log mean, it is between the surface and the water. All right. So what we need to find it out is we need to find out this, the convection coefficient, the convection coefficient. And by the way, if we write this way, the overall transfer rate is equal the hot water plus the air. Why is all of a sudden it's yeah, if this is what we write, and then I'm just go ahead to find the convection coefficient of the water and the convection coefficient of the air. So in order to calculate this convection coefficient, we would have to use these equations, and this is the internal one, and then the external one was given to you previously. In order to calculate those, we would have to have Reynolds number, and then Luceno number, Plano number, and all these that requires a assumption of the surface temperature, or a temperature at which we can take the property of the fluids. Alright, first we have to take a gas, and then we assume the surface temperature is somewhere in between the hot water and the cold air. So really up to what you take. So I typically start with the average of the two. Let's say the hot water temperature and the air temperature divided by 2. And you don't have to take this, and you can take something more reasonable. Let's say if you don't believe if you think the convection coefficient in the water is much higher than the air, then you can have a surface temperature closer to the hot water. If you think the other way around, then the surface temperature can be closer to the air temperature. But here I just take the half, that will equals to T plus 16, that is 35C. 35C, that is equals to 308K. And then if you look at the table, oh no, this is the surface temperature, by the way. I don't even need to calculate to the 300K yet. And then for internal flow, for the hot water side, then the T average hot water, it is the average between the surface temperature and then the temperature of the water, the mean temperature of the water, that is 60, 35, that would be 47C. That is equals to 320K. And for air, the average temperature of the air, that is equal to the Ts plus T infinite half, then that would be 37 plus 10 divided by 2, that is 22C. That is about 295K. All right. So now we need to look for the property of the hot water and the property of the air. So for the hot air, we'll have 295K. So we can roughly use 300K. So I just copy from here the density, the heat capacitance, the viscosity, the conduction coefficient, and then the Prandtl number. For the water property, it is the appendix 8.6, and we have 320K, so that's where this is. So you can get all the properties at 320K. For the hot water side, then the density is 1 over the number that you get from the table, that is 989 kilogram cubic centimeter. And then you can calculate the Reynolds number of the water inside the pipe, that is get 686. This is actually much smaller than 2300, and then therefore it's laminar flow. Because it's laminar, and also because the surface temperature is a constant, then we look up for the PDF. There are two cases. One is the heat flux is a constant, and the other case is the surface temperature is a constant. For the surface temperature being a constant, the Nusselt number is always a constant 3.66, and therefore the convection coefficient is 3.66 times the conduction coefficient of water divided by the diameter, and this gives you can just put it back. The conduction coefficient was given from the table, 0.64, and then the diameter is 2 centimeter, and you get 139.5 convection coefficient. And if you want, you can put a bar there on the convection coefficient of water. You don't have to, but I typically put here. And then this is the convection coefficient of the water. In order to calculate the convection heat transfer rate from water, we need log mean, and we don't know the outlet temperature yet, so we cannot use this. And then the other one is the air side. At the air side, the temperature average we already calculated is 22 C, about 300 K. So we can read the density of the air, and you can calculate the Reynolds number. And for this cross flow outside, external cross flow of the pipe across the pipe, we had a handout a few classes ago, and then from the Reynolds number, the C equals to 0.683 and M equals to 0.466. And now you can look at Nusselt number definition, the convection coefficient to 22.3. And from the outside, we can directly calculate the Q. From the outside, you can directly calculate the Q. Q equals to the convection coefficient times the surface area of the pipe, and then times the surface temperature minus the air temperature, or the infinite temperature. And if you punch in all the numbers, 7 watt. If the Q equal to 7 watt, then if the Q equals to 7 watt, then this Q would have to equal to the Q water as well. Q hot water. Q hot water, that is equals to the average convection coefficient at the hot water side, and then times the surface area times the log mean between the surface and the water. Or you can use the other overall convection coefficient, overall transfer coefficient, and then use the log mean between the outside and the water. It should be the similar thing, just a little bit more complicated to calculate the U from the 2H. Here I just use the internal side. That equal to 7 watt, so therefore I can calculate the log mean, right? And this log mean equals to Q divided by the convection coefficient and then the surface area, and then you can calculate that difference. The log mean equals to 4C. And then one thing here is log mean also equals to the inlet temperature difference is the water temperature at inlet minus the surface temperature. The surface temperature is constant, does not depend on the location, so I don't have to put an inlet surface temperature. It is same number, and that equals, so 4 equals to delta T minus 25, and then log delta T over 25. Outlet temperature difference between the surface and the water is only 0.05 C. So this T equals to the water temperature at the mean at the outlet minus the surface temperature, right? And this actually, according to what we calculate, should be equal to 0.05. So we need to calculate this guy. So basically, as you can see, the purpose of doing this is we assume a surface temperature at the beginning. So we assume a surface temperature, and then we are trying to confirm this surface temperature after the calculation. And then, however, in order to get this surface temperature, we have to get this outlet water temperature. And then the outlet water temperature has to be calculated from the energy balance. That's what we talked about here. Maybe I should use a different color. So here, and then we can calculate this way. So equals to, yeah, if the Q equals to this, then the Q should be equal to the hot water in minus the hot water out. And then yeah, because the water is being cooled, so the inlet temperature minus the outlet temperature. And then Therefore, the outlet temperature, and M is the mass flow rate, density times the volumetric flow rate. Volumetric flow rate, that equals to the velocity times the cross-sectional area of a pipe. And then that is, if you punch these numbers, and the CP is also given in the table we already got previous. It's 4180 here, and then you can calculate temperature difference between the surface and the outlet water is at outlet is 0.05 C. So the surface temperature at the outlet is only 0.05 C. Above the water temperature is 59.35, and then as you can see, this is different from assumption. Therefore, need to reiterate. So now we have choices how to choose another temperature, and you can choose 35, or you can choose 59, saying that if the surface temperature equals to 59 here, then you can do another round. But I probably choose something in between this first assumption and then the first calculation. Hopefully that can speed up a little bit things. So I'm not gonna take another assumption. So assume, we know that the first assumption is too low because the first calculation is much higher. And then if I take the first calculation, that might be too much because that is based on a low temperature assumption. So I'm just assume I will take another assumption. Let's say assume somewhere in between these two. Assume the surface temperature equals somewhere in between 35 and 59. So let me say if it is if I average, that would be 35, 59, that would be 47. Yeah, 47. So if it's 47, I just take 50. 50 C. Assume the surface temperature is 50 C. Then look for the properties. 805. It is still laminar. 3.66, and we can calculate the water side, the convection coefficient. That's the hot water side. And then for the air side, we have to look up for the property of air at a temperature 308 K. I'm gonna take everything from 300 K on the table, and then at 300 K, and then we have to recalculate the Q. Q, however, is now different. The heat transfer rate is 11.2 watt. Then we can calculate, therefore, for internal hot water flow, delta log mean between the surface and the hot water that is Q, and this equal to 5. So therefore, and then times the cross-sectional area. And then minus 5.5, that is about 54C. So as you can see, we assumed a surface temperature of 50C, and now we arrived at temperature of the surface at 54, close to assumption. You can I take ES equals to 53.